Hey, Calculus, here's part 5 of the area section. It's going to be the last one. Let's hope we can get through this efficiently. Last time, we said that the area of the upper and lower sums are actually going to be the same thing as long as n goes to infinity. So what this new theorem down here says is that if I want to find the area under a curve, I'm going to take the limit as n goes to infinity of the base times height of each one, and that's ci. That's saying that it can be anywhere in that interval. So in the ith interval between the x sub I minus 1 and the interval and the x sub I after that, any number in that interval will work. Here's an example. Here's my interval. Here's one interval. Any value of x in this interval will work. It doesn't matter which, as long as the value of n approaches infinity. So whether it's the lower sum, the upper sum, or anywhere in between, it doesn't matter. So this is going to save us some time. If I just want some arbitrary ci in some interval, the formula a plus delta x times I, that's going to be what we're going to use just to make things a little bit easier. Maybe there's some easier ways to get a point in the interval, but that one's always going to work. So here we go. Take a second to copy it down. Finding area by the limit definition. Find the area of the region bounded by the graph f of x equals x cubed. The x-axis and the vertical lines x equals 0 and 1. So here we got from x equals 0 to 1, this region right here. Just by looking at this ballpark, the area of that square is 1 by 1, so it's 1. This would be like half of 1. This would be a half the area of each triangle. So this is going to be less than that. So I don't know. But it looks like it's going to be less than 0.5, the area of this little pink region. Let's see. All right. So I need to find, if I want to find the area, that's going to be the limit as n approaches infinity of the sum, I goes from 1 to n, of, it was delta x, doesn't matter which one you go first, it's multiplication, it is, okay. The height, which is f of x, where x is some number in the interval, we'll call it c, times the width, delta x. So let's go find those. Delta x is b minus a over n. So we're going from 0 to 1, so it's going to be 1 minus 0 over n, which is 1 over n. And I told you for ci, let's just use the general formula. I said it was a plus delta x times I. A is 0, so it's going to be 0 plus delta x. We said it's 1 over n times I, which is really just I times 1 is I. It's I over n. So here we go. So the limit as the number of rectangles approaches infinity of the sum of all of these rectangles is going to be f of ci, which we said ci is I over n, times delta x, which I said is 1 over n. Alrighty, let's do this. So I'm taking the limit of the sum, which, by the way, in itself, taking a sum is a big deal. It's not an easy thing. Taking the limit of it, this is some wild stuff that we're doing. So don't, give yourselves a pat on the back. This stuff isn't easy. My function just cubes its input. Its input is I over n. And what do we get? The limit of the sum, I over n cubed, is I cubed over n cubed times 1 over n. So we still have the limit as n goes to infinity. N cubed times n is n to the 4th. And in regards to the summation, I could factor out the n to the 4th. That's just a constant with regards to I. So we just have the sum of I cubed times 1 is I cubed from 1 to n. I can't factor the n out of the limit because the limit is as n approaches infinity. That's not a constant with the limits perspective. So we get the limit as n approaches infinity of 1 over n to the 4th. Now the formula for I cubed, we'd have to go back up to the top, but It's actually not terrible to remember. If you remember the formula for I, it was n times n plus 1 over 2. The formula for I cubed is just squaring that. N squared over n plus 1 squared over 2 squared, which is 4. So, maybe it's an easy way for you to remember it. Maybe it's not. All right. A little simplifying we can do here. This n to the second, we'll take out 2 of those n's, so I just have 2 on the bottom. I'm going to factor that 4 out of the denominator just so we don't have to deal with that fraction. So I have the limit as n approaches infinity of 1 over 4. Take that out. We still have n squared down here. What was left over is the n plus 1 squared, which is not n squared plus 1. You got to FOIL it. Please don't forget to FOIL it. That's going to be n squared plus 2n plus 1. Talking to you, Bert. All right, so we get the limit as n approaches infinity. Now we just got to distribute. So 1 times n to the second is n to the second. 1 times 2n is 2n. 1 times 1 is 1. Nice little color palette here. What simplifies? The n's are going to cancel out. This n's going to take out one of those n's. And then we get, we get the limit as n approaches infinity of 1/4 plus 2 over 4 is 1/2. 1 over 2n, this n took out one of those n's, there's still an n left over, plus 1 over 4n to the second. And as n goes to infinity, these two things are going to approach 0. And 1/4 is going to stay as 1/4. So this is going to become, the area under that curve is exactly 1/4. Now you can celebrate. We did something really difficult. We found the area under a curve, not just an approximation, but the exact area under that curve is 1/4. Now I'm sure you're looking to try one on your own, so here's one opportunity. Before you do that, maybe we set it up together. If you want to run through it on your own, give it a try. So the function needs to be continuous and non-negative. It is continuous and it is non-negative. We'll actually deal with negative functions later on when it's below the x-axis, but right now it's not important. We're defining area as a positive number. So if I want the area, I'm going to need to find out what delta x is. Delta x is b minus a over n. Well, let's see. Find the area. The graph is 4 minus x squared, and we're going between 1 and 2. So b minus a over n is just 1 over n. So the width of the interval is 1. I'm going to divide it into n subintervals. For CI, let's just use that formula, a plus delta xi. A is 1. Delta x is 1 over n. And multiply that by I. This is going to be a kind of a pain. When a is 0, it's a little bit easier to work with. But now that I have a 1 plus 1 over ni, now we're going to have to FOIL again. But so be it. Let's go blue again. So if I want the area, it's going to be the limit of the sum of f of ci delta x, which we know what those are. I mean, they're more variables. We know a variable in terms of another variable, but for this problem, we can at least rewrite ci as 1 plus I over n. 1 times I is I, so I'm just going to write that as 1 I over n. Delta x is just 1 over n. And my function is 4 minus x squared. Ooh, not looking pretty. All right. X cubed was nice. This one is asking us to do some math here. So my function times 1 over n. Okay. So my function, when I plug in 1 plus I over n, it's 4 minus that input squared. So it's going to be 4 minus that input squared, that input being 1 plus I over n. That's my input. Okay. How bad was that? I'm still breathing. I think it wasn't too bad. So we have the sum where I goes from 1 to n. All right. Yeah, let's FOIL. It's gonna be 1 plus 2I over n plus I squared over n squared. You can check it, and that's times 1 over n. Yeah, that's what I got. And this negative is going to get distributed in, so that's going to make that a minus, and a minus. Be careful with that. 4 minus 1 is 3. I'm going to factor this 1 over n out of the sum for now. Just get it out of there. So 4 minus 1 is 3. Minus, let's see, we have 2 over n times I. Minus I squared over n squared. And I'm taking the sum of all that. All right, so I'm going to distribute that sum into each of these and use my sum formulas. This is the limit as n goes to infinity of 1 over n times. Okay, so the sum of 3, if I add 3 up n times, that's just 3n. Now 2 over n is a constant, so I'm just going to factor that out. And the sum formula for I is n times 1 more than n over 2. This n squared I can take out. That's just a constant with the in terms of the index. And the formula for I squared is n times 1 more than n times double n plus 1 all over 6. Whew. All right. If you had to look up back at the formulas for that one, I don't blame you. That's not easy. So now we got the limit as n approaches infinity. I have 1 over n. I don't know, man. It's just a lot going on here. Let's just one step at a time, I guess. I'm going to leave the 3n alone for now. Let's see. These 2's cancel out, and these n's divide out. So that's nice. We just going to have a... Don't forget there's a minus here. It's going to be a minus n minus 1. That negative will really get you. What else happens here? This n is going to take out one of those n's. And why don't... what do I want to do with that 6? Let's just rewrite this as minus 1 over... Let's just take out the 6 for now. So we have the... that n took out one of those n's, so there's still an n left over. And then when I FOIL the n plus 1 times 2n plus 1, that's 2n squared plus 3n plus 1. Not bad, not bad. We're getting there. Ooh, I see one thing that I did on my answer key that I didn't do this time. That's okay. I factored out an n. Where? Well, it's not going to matter because I took that one out. All right, so we have 1 over n, 3n minus 2n, 3n minus 1n is 2n. So that takes out those two. Minus 1. Let's distribute this in. Why not? Let's see. This is going to give me 2n squared over 6n. This is going to give me, so that was the first one. The second one, it's going to give me a minus 3n over 6n. And last but not least, it's going to be minus 1 over 6n. Another distribution here. Let's stick with purple. Multiply everything here by 1 over... That's not purple. Let's multiply everything in here by 1 over n. Actually, let's not do that yet. These ends are going to cancel out, and this end's going to take out one of those ends. Let me just write what we have before I distribute that end. All right, so I have 2n minus 1 minus 2 over 6 is 1 over 3. There's still an n up top. 3 over 6 is 1 over 2. And I hope I didn't make a mistake. Now distribute that 1 over n. So 1 over n times this can just give me the 2. The ends will cancel out. This will give me a minus 1 over n. Keep going. The ends will cancel out. I'll just get minus 1/3. Same thing over here. It's going to give me minus 1 over 2n. And this is going to give me a minus 1 over 6n squared. Whew! Do we have it? Let's find out. I know the final answer should come out to be 5/3. Let's see if I have to make another video here. That's going to approach 0, that's going to approach 0, and that's going to approach 0. So I'm just left with 2 minus 1/3. 2 minus 1/3, which is really, let's see, 3 times 3, so it's 6/3 minus 1/3. And that's 5/3. There you have it. The area under the curve. See if you guys got 5/3 or 1 point, whatever, 5/3. 1 point, that's 1.6 repeating? I don't know. Anyways, a lot of work to find the area under a curve. And I know what you're all saying to yourself, Mr. Florio, if there is only an easier way, I mean, what was the whole point of that whole antiderivative stuff? Well, that's all for section 5.2 area. I'm going to leave you out with a story. The function party. So there's this function party going on, and all of the hippest functions are there having a good time. Cosine x is getting down and dirty with the natural log of x. 10 to the x is making the moves on the x minus 2 squared twins, and even x factorial dragged himself out for a good time. Unfortunately, one little function just wasn't having her night. E to the x was sitting in a chair in the corner, tears dripping down exponentially. Sine of x catches her out of the corner of his eye and decides to cheer her up. Come on, E to the x! Exclamation point. There's no reason to sit all on your lonesome crying. Get out into the crowd and have some fun. You know, integrate a little bit. E to the x looks at sine of x with the saddest eyes and exclaims, but it won't make a difference.